Now we will talk about how to label crystal planes and directions. First, I'm going to demonstrate it for a cubic crystal, then we will talk about a hexagonal lattice structure. So as for the directions, we have a lattice vector, any lattice vector that takes us from one lattice point to another lattice point, R vector that is written in the form n1a1 plus n2a2 plus n3a3. n1, n2, n3 are integers, a1, a2, a3 are our basis vectors. Then we will refer to the direction of this vector as a set of indices called the Miller indices shown in square brackets HKL, such that these numbers HKL are n1, n2, and n3 reduced with their highest common factor. So the coefficients n1, n2, and n3, we find their highest common factor, we divide them by the highest common factor and reduce them to the numbers HKL respectively. So here is one example. We're looking at this lattice translation vector a1 plus a2 plus 0 a3. So that is this vector at the bottom, and because the coefficients are 1, 1, 0 and the highest common factor is 1, we will have for HKL 1, 1, 0, and we will label this with square brackets 1, 1, 0 direction. And actually, if you look at the symmetry properties of the crystal, we will find that a direction actually represents a set of parallel vectors equivalent by translational symmetry. So we can refer to a family of directions that are equivalent by symmetry in a cubic crystal. If there are non-parallel vectors which are equivalent by symmetry, then such equivalent set of directions will be indicated by angle brackets. So that is angle brackets HKL. So this should be an angle bracket here, HKL. So for example, 1, 0, 0 set of directions actually represents 6 directions. 1, 0, 0, 0, 1, 0, 0, 0, 1, 1 bar 0, 0, 0, 1 bar 0, and 0, 0, 1 bar. So those are, if you look at the cubic structure here, 1, 0, 0 is the red one, 1 bar 0, 0 going back is actually equivalent because this is a cubic crystal, and similarly 0, 1, 0 is equivalent to 1, 0, 0 by symmetry, etc. So we see that all these 6 vectors are equivalent by symmetry, so they belong to the family of directions 1, 0, 0. Another example is here. Here's a lattice translation vector 2a1 plus 6a2 plus 4a3. So we take these coefficients 2, 6, and 4. The highest common factor is 2 here. Highest common factor is 2. So we divide them by 2. 2 over 2, 6 over 2, 4 over 2. We obtain 1, 3, 2. So in square brackets, we label this direction 1, 3, 2. Okay. Now, as for the planes, the orientation of a plane is also specified by the Miller indices HKL, and here is the procedure. So you're given a plane, you want to label it. The first thing you have to do is find the intercepts of the plane with the axes using basis vectors a1, a2, and a3. And if these intercepts are x, y, and z, we will work with that. So let's demonstrate this with an example. Here is a plane. The intercepts are here at b over 2, you can see, and here at minus a over 2. And the other intercept would be at infinity. So why is it a over 2 and b over 2? Because the distance between two lattice points on the y-axis are b, on the x-axis are a, on the z-axis are c. So you will have, therefore, a1 vector here is a I hat, a2 vector here is b j hat, and a3 vector here is c k hat. So the because the intercepts are exactly in between these two lattice points at the center, so the intercepts are at minus a over 2, b over 2, and c. So for this example, x is minus a over 2, y is b over 2, z is infinite with the basis vectors ai hat, bj hat, and ck hat. Next, we form this set of numbers x over a, y over b, z over c. So we have minus a over 2 divided by a, b over 2 divided by b, infinity divided by c. That becomes minus 1 over 2, 1 over 2, and infinite. And then we invert the triplet so that it becomes a over x, b over y, c over z. So minus 1 over 2 inverted becomes minus 2. 1 over 2 inverted becomes 2, so it's 2 over 1 is 2. And infinity inverted, 1 over infinity becomes 0. So minus 2 to 0. And then we reduce this set by dividing with the highest common factor. So the highest common factor for these is 2, minus 2 and 0, they have a highest common factor 2. So when we reduce it, we get minus 1, 1, 0. And we label the plane using parentheses HKL, so it becomes minus 1 becomes 1 bar, 1, 0. Notice that we don't have the comma in between these numbers, because if you put comma in between numbers, that usually represents a point in space. So in Miller index notation, there is no comma. Okay, so we have successfully labeled this plane 1 bar, 1, 0. Now the planes that are equivalent by virtue of symmetry are labeled using curly brackets, so that is a set of equivalent planes. So similar to directions, we have a set of equivalent planes that we can talk about, and I will give an example here. Now I have a few remarks. If the plane is parallel to an axis, the intercept is at infinity, as we have seen in this example. The corresponding Miller index will be 0. If the intercept is negative, we use a bar over the corresponding index. As you can see here, minus 1 was replaced by 1 bar. And number 3, if the intercept is at 0, we translate the plane to obtain a non-zero intercept. So we avoid 0 intercepts. So let's demonstrate this here. So we're looking at this blue plane. The blue plane has intercepts with the x and y axis at 0, 0, and with z axis at infinity. Okay, so the procedure says if the intercept is at 0, you need to translate it. So let's translate this on the x-axis by one lattice constant. So it was intercepting at 0, now it's intercepting at 1 on the x-axis. So with that, you can see, since this is a plane that goes through 0, 0, 0 and 1, 1, 0, it actually is going to intercept, the new translated plane will intercept the y-axis at minus 1. Okay, so the new intercepts will be 1, minus 1, and infinite. So highest common factor is 1. I divide it by 1, and then I take the invert the ratio, so that it becomes 1 minus 1, 0, because 1 over infinity is 0, and I label it 1, 1 bar, 0. So this plane, this blue plane, is actually 1 bar, 0. Now, if you look at this red plane, that red plane intercepts x-axis at 1. So let's put lattice points here. As you can see, this intercepts at 1. So these are my lattice points. And also x-axis and y-axis at 1, z-axis at infinity. So it's a 1, 1, 0 plane. Now, if you look at the symmetry of this crystal, 1, 1, 0 plane and 1, 1 bar 0 plane are equivalent planes. They belong to the set of equivalent planes 1, 1, 0. So we show it with curly brackets. Now we see that 1, 1, 0, 1 bar 1, 0, 1, 1 bar 0, and 1 bar 1 bar 0. These are all equivalent planes by virtue of symmetry. So we can represent this family of planes with the curly brackets 1, 1, 0. Now, in a cubic crystal, we find that the HKL direction is always perpendicular to the HKL plane. So for example, if we have a 110 plane here, that is this red plane. So look at the 110 direction now. So where is the 110 direction? So 110 direction is this direction. That is 110 direction. And as you can see, this is going to make a 90-degree angle with respect to 110 plane. So this is a general feature we find in cubic crystals. Now, what is the distance between the parallel planes of a cubic crystal? Actually, I'm looking at the nearest parallel planes. So to find this, let's consider two parallel planes, one of which goes through the origin. So I have two planes. One plane is going through the origin. The other plane is intercepting x, y, and z axes at points x, y, and z. Okay, so this is the intercept at x, the intercept at y, the intercept at z. And then I have another plane which is going through the origin. Okay, so we're considering two parallel planes here. One includes the origin, the other one does not. Okay, the second plane, HKL, makes intercepts A over H, B over K, C over L by definition of Miller indices. So this X, Y, and Z here are A over H, B over K, and Z over L. So now, since this direction HKL is perpendicular to the HKL plane, the distance between the origin and the plane is the length of the vector pointing in the HKL direction. So I look at the length of the vector, so this is OP vector, between the two planes, and if you look at the angle this vector makes with the x-axis that I called alpha, here I show it, OP vector makes an angle alpha with the x-axis. The distance between the two planes is d, which is the magnitude of the OP vector. And so this triangle, from this right triangle, I can see that d is x cosine alpha. The same thing is true for y. D is y cosine beta and d is z cosine gamma. So these alpha, beta, and gamma are directional cosines. So alpha, beta, and gamma are what we call directional cosines. So those are the angles that we make with x, y, and z axes. Okay, so since x is a over h, y is b over k, and z is c over l, and we have law of cosines. Law of cosines for direction cosines, cosine square alpha plus cosine square beta plus cosine square gamma is 1. So cosine alpha is d over x, d square over x square plus d square over y square plus d square over z square equals to 1. And for x, y, and z, I substitute a over h, b over k, c over l. And then I note that for a cubic crystal, what I called a, b, and c are the same thing. So I can replace a, b, and c with a. Therefore, I find that the distance between two parallel planes is a divided by, a is my lattice constant, square root of h square plus k square plus l square. So what is this again? Distance between two parallel HKL nearest neighbor planes. Okay. Now, last but not least, let's talk about Miller indices for hexagonal lattice. Well, there I have, I can talk about 4 basis vectors, A1, A2, A3. So those are at angles 120 degrees with respect to each other. So all these angles are 120 degrees. And there is the C vector, which is the vector that points from the middle to the top of the hexagon. So we have 4 vectors. And so I'm trying to label a plane here so that there's this purple plane. It intercepts the A1, the axis that contains A1 vector at 1A1 and 1A2. it doesn't intercept A3, and it's parallel to the C-axis. So intercepts are at AA. For A3 vector, which is pointing in this direction shown by the green arrow here, I see that this actually goes through and intercepts the axis that contains A3 at minus A3 minus A over 2. So this intercept is at minus A over 2, and the z-axis, it's parallel, so it doesn't have an intercept with the z-axis, the axis that contains c vector. It's at infinity. So I take the reciprocals, 1 over a minus 2 over a 0, and so I'm going to label this that because a is the common factor here, so they're reduced. So I have 1, 1, 2 bar 0 plane. So this purple plane is 1, 1, 2 bar 0 plane. So I can use 4 indices with these 4 vectors. Now for directions, the 3-digit notation is as follows. First of all, I want to note that A1, A2, and A3 basis vectors are not linearly independent. So in a sense, they're not basis vectors because they're not linearly independent. So A1 plus A2 plus A3 adds up to 0. So if I have a lattice translation vector which is minus A1, I can write this as minus A1 plus 0 A2 plus 0 A3. So that would be 1 bar 0 0 direction using my convention in cubic crystals. So that's HKL direction. But because I have introduced this 4-digit notation for hexagonal lattices, we have a transformation from this HKL to HKIL, so that the corresponding Miller indices are capital H equals H minus I, capital K equals K minus I, capital L equals L, and these indices H, K, and I add up to 0. So if I have, using the cubic crystal convention, 1 bar 0 0 vector in a hexagonal lattice, how can I represent it with the 4-digit notation? Well, H minus I is minus 1, so H is I minus 1. K minus I is 0, K is I. H plus K plus I is 0. So I minus 1 plus I is 0, so I is 1 over 3, and L is 0. So I is 1 over 3, H is I minus 1, which is minus 2 over 3, K is I, which is 1 over 3, and L is 0. So I have minus 2 over 3, 1 over 3, 1 over 3, 0, and 3 is the highest common factor, so I can get rid of that. So basically I will obtain 2 bar 1 1 0 direction. So I see that 1 bar 0 0 direction, which is in the minus A1 vector direction, this is represented by 2 bar 1 1 0 using this notation. How about the 2 bar 1 1 0 plane? So where is the 2 bar 1 1 0 plane? Well, that has to intercept the A1, the axis that contains A1 vector at minus A over 2, the one that contains A2 vector at A, A3 vector at A, and the C axis at infinity. So I find that I have to go to minus A over 2 here, so that's the intercept here. So this is at this is my minus A over 2, and then I have plus A and minus A, so those 3 intercepts, and intercept at infinity, so parallel to the C-axis, so that is 2 bar 1 1 0 plane. And I noticed that 2 bar 1 1 0 direction, which was the minus A1 vector, is perpendicular to this, so 2 bar 1 1 0 direction is perpendicular to 2 bar 1 1 0 plane. So using this 4-digit notation also for an hexagonal lattice, I find that the HKLI direction is perpendicular to HKLI plane. So this feature that I had in cubic crystals is also satisfied if I use this set of transformation equations for the 3-digit to 4-digit representation. Okay, so we have talked about how to label planes and directions using Miller indices. So given a lattice translation vector, we can find the directions by looking at the coefficients, reduce them with the highest common factor, and take the reciprocal and label the plane with square brackets. The set of directions that are equivalent by symmetry are labeled using angle brackets. And we have gone through an example here. And for planes, we find the intercepts with the xyz axis, the axes that contain the basis vectors a1, a2, a3. And those intercepts, we look at the ratio x over a, y over b, z over c, take the reciprocal, we invert the triplet, divide it by the highest common factor to reduce it to a set of numbers HKL. If you have a negative intercept, we use a bar. If we have an infinite intercept, that means the parallel to the axis, we have a 0 Miller index. If the intercept is negative, we have the bar. If the intercept is at 0, on the other hand, we translate the plane to a non-zero intercept. The parenthesis was used for a single plane, curly brackets for set of equivalent planes, and we have gone through an example here. We have seen that if the intercept was at 0, 0 and infinity, we can translate it on the x-axis. We could also translate it on the y-axis, doesn't matter. We would obtain a parallel plane. So we label that plane using this, the new intercepts. Okay. And in the cubic crystal, we have this property that HKL direction is perpendicular to the HKL plane, and the distance between two parallel planes in the nearest parallel planes in a cubic crystal, we find using cosine theorem, law of cosines, that it is a, the lattice constant of the cubic crystal, divided by square root h squared plus k squared plus l squared. For hexagonal lattices, we have a 4-digit notation, HKIL, and for the planes, we again follow the same procedure. We find the intercepts, take the reciprocals, reduce by lowest common factor, highest common factor, and label the plane using parentheses. And for directions, we can start with the 3-digit notation using a1, a2, a3 vectors, for example, if it's on one plane. And we can see that we can go from a 3-digit to a 4-digit notation with this transformation equations. And we find that if we use this transformation, the direction that we obtain is perpendicular to the plane with the same set of Miller